going to talk about long horizon control with learned models. So I'll kind of keep the motivation actually pretty short. So if we want to start thinking about autonomous learning of behaviors, at a very high level, we basically need to figure out kind of two things. We need to figure out algorithms and representations. And in a lot of my work, and a lot of other work recently, a very useful place to look for algorithms is the field of reinforcement learning. So this provides us with a mathematical formalism for learning-based control, where you have an environment and an agent, which in our case will be a robot. The robot chooses actions and the environment responds with states and consequences of that behavior, which are rewards. And then the agent's goal in reinforcement learning is to acquire a policy, which we would denote as pi of A given S. It's a distribution over actions condition on states. And the goal is not just to get a policy that gets high rewards greedily, but one that gets high reward in expectation, summed over the entirety of the episode or the entirety of the agent's existence. So usually when we think about reinforcement learning, we think about it as a very kind of kind of a controller learning focused framework, not necessarily so much a planning framework, although the two turn out to be actually pretty similar. Of course, if we want to actually instantiate it for complex real-world robotic systems, we also need to select representations for things like policies, value functions, etc., and a very powerful class of representations that we know works quite well is large high-capacity deep networks. So these kinds of representations have been very effective in supervised learning domains that require a lot of generalization, like computer vision, translation, speech recognition, and so on. So perhaps they can also be successful in robotics. At a very high level, this basic formula appears to work to some degree. So it appears to do something useful. I'll show a few examples from my past work, although there are many, many other examples as well. Here's an example of a deep reinforcement learning framework that we developed a couple of years ago with colleagues at Google for robotic grasping. And this was a system that could use images from an over-the-shoulder camera. You can see the camera in the video. It's a little black box at the top. The resulting grasping system, trained entirely with DeepRL, was able to do some pretty interesting things. It could pick up objects in dense clutter, pick up transparent objects, soft objects, etc. So it really generalized and it worked decently well. But these are not really long horizon tasks. Here the task is to pick up one object at a time. A few other things we've done. This is a three-finger hand learning how to open a door. This work I'll actually talk about in a little more detail later on today, but this was a project that my student Usha Nagabandi did on getting a five-finger hand to twirl two objects in the palm. But again, these are fairly short horizon tasks for now. Outside of manipulation, the basic recipe also seems to do something sensible in navigation and mobility tasks. This is a ground robot navigating a forest from vision, again, trained using DeepRL. And here the DeepRL system is actually predicting whether it'll have a bumpy ride or whether it'll collide with objects, as you can see in this visualization. Also, the same basic recipe can be used for robotic locomotion. So this is a project that was done by my student, Jason Peng, in collaboration also with colleagues at Google, where Jason was able to demonstrate that he could get this four-legged robot to do some cool jumps and runs and so on. But of course, in keeping with the topic of this workshop, the thing that I'm actually going to focus on today is how we can move from this kind of recipe, which seems to learn individual skills, to longer horizon planning. So to kind of provide a little bit of an analogy for this, this is a map of the San Francisco Bay Area. So the bicyclist there begins in Berkely, right next to where I live. And let's say that my goal is to ride that bicycle over to the Golden Gate Bridge, which is that orange bit on the left side. If I just learn kind of a bicycling skill, that might be very nice for getting me to be able to ride the bicycle up a hill, down a hill, around a left turn or a right turn. But it seems like a little bit of a stretch to imagine that the same kind of skill, if I just train it for long enough, will basically master the navigational part of this task to bicycle all the way to the Golden Gate Bridge, reasoning about things at the level of individual muscle movements and pedal movements. So perhaps if we really want very temporally extended behaviors, we need to really think about how these kinds of learned skills, which seem to work quite nicely for closed loop control in these shorter horizon problems, can actually be extended to solve much longer horizon problems. So that's the topic that I'm going to try to discuss in today's talk. Can we utilize reinforcement learning essentially as a sort of primitive in performing long horizon planning? All right, so I'll split this talk into three parts. First, I'll talk about how we can plan with deep predictive models, and this will not be long horizon. This will be fairly short horizon, just to get us comfortable with the notion of how we can combine learning and planning, and why that might be a good idea. Then I'll talk about how we can learn low-level skills with deep RL automatically without being told in advance what skills are useful. And then I'll put the two together and discuss how those learned skills can actually be combined with a kind of a planning style procedure to solve longer horizon problems. So you can sort of think of the first and second part as describing the ingredients, and the third part as putting those ingredients together. All right, let's start with planning with deep predictive models. So the basic recipe, and this is basically the recipe behind model-based reinforcement learning that I'm going to discuss, works like this. You collected some data from your past interactions, and model-based RL algorithms, fortunately, are usually very comfortable with off-policy training, so it's okay if this data came from a different policy. And formally, we'll say that this data consists of tuples, S, A, and S prime. You're going to use those tuples to train a predictive model. So this is a model that estimates the distribution over the next state, P of S prime, given S comma A. And then you'll use this model for control and potentially go out and get a little bit more data to improve it. So the model would be represented with some high capacity representation, like a deep neural network, that takes in the current state in action and outputs the resulting state ST plus 1 or S prime. And typically we would train this model with just regular supervised learning, maximum likelihood. So there's nothing really fancy about how the models are typically trained, although there's maybe like a few delicate choices to get them to work well in practice. So then once we have this model, we have a few choices to make in terms of how we use it for control. We could use it to train a policy, but what I'm going to actually focus on today are methods that actually use the models directly to plan actions. So at a very high level, you can imagine the action planning problem as being the one that's written kind of in the lower left of this slide. Select a sequence of actions A1 through AH that maximizes the conditional expected value of the reward given those actions. And the expectation here is taken under this learned model. So this is what I'm going to refer to as planning, essentially solving this maximization problem. And there are many algorithms that we can use for this. I'm actually going to use very crude, very simplistic algorithms. There are much, much better ways to solve this planning problem. I'm kind of less concerned about how you solve it and more concerned with the whole setup surrounding it. Very crudely, you could imagine this process of selecting the best actions as basically considering a few possible action sequences, maybe modifying them in some way, whether it's using a stochastic search or RRTs or whatever your favorite algorithm is, and then eventually selecting the best one, the one with the best reward. A very important detail in practice is that if you want to actually use methods like this, it's a very good idea to do model predictive control, where you replan your action sequence every step, because that does a lot to mitigate some of the errors that would be due to incorrect models. Which planning or optimization method should you use? I'm probably the wrong person to ask that. I think there are people in this workshop who can give much better answers. I'm going to use the cross-entropy method because I know how to implement that in 3 lines of code. It's not by any means the best one. There are much better choices, but that's what I'm going to use. All right, so does this basic recipe work? So we started studying this a few years back. One of the things we discovered pretty quickly is that if you just train a single predictive model, just a neural net, like I described on the previous slide, that actually doesn't tend to work so well because it's very easy to find states and actions that are out of distribution for which the model makes erroneous predictions. But what does turn out to work quite well, and is a very simple modification, is to use a bootstrap ensemble where you train multiple models on different resamplings of the data, and then use the agreement or disagreement between those models as a measure of epistemic uncertainty. Essentially, try to get your planner to go to places where the models agree. That greatly mitigates the problem of out of distribution states and actually makes this basic recipe more or less work. So this was a paper that we published a couple of years back called Deep Reinforcement Learning in a Handful of Trials Using Probabilistic Dynamics Models, where probabilistic refers to their ability to estimate epistemic uncertainty. And we compared it on a bunch of standard kind of RL benchmark tasks and found that the the scheme actually worked quite well. So here the blue line shows this method, which is called PETS. The dotted black line shows the performance of PPO at convergence. The other black lines show other model free RL methods at convergence, whereas the colored lines show how they actually do in terms of the number of time steps. And for example, on this task, this method exceeds the performance of PPO after about the equivalent of 10 minutes of real time. It's several orders of magnitude faster. So you get a pretty big improvement in terms of sample complexity from doing this. But usually that comes at a cost in asymptotic performance, especially on the harder tasks. So you can see that the state-of-the-art model-free method here, soft vector critic, the dotted line at the very top does do quite a bit better than PETS. All right, so in some recent work, this is work led by my student Anusha Nakabandi, we wanted to study how these kinds of model-based RL methods can be applied to dexterous manipulation, and in particular, better resolve the question of when should we prefer model-based RL. So one of the things that Anusha found is on narrow tasks where you basically have to do just one thing, model-free RL tends to do very well. So Anusha set up this task where a 5-finger hand needed to use a pencil to draw a character. In this case, it was drawing a 0. And she found that, while there are big differences in sample complexity, everyone basically solves the task at the end, at least if they're kind of good state-of-the-art model-free methods. So the little green line that just shoots up here, this is the model-based method that Anusha developed called PEDM, and it gets to maximum performance very quickly, but the model-free methods get there too. They just take a little bit longer. However, if you increase the diversity of the tasks, then it actually often turns out to be the case that model-based RL has a bit of an advantage. So when Anusha changed this task so that the hand needed to draw different digits on the paper, so it's kind of drawing different kind of MNIST style digits, 6s, 9s, 1s, etc. And in particular, we want the same model to draw every kind of digit by taking the digit as an input. Then actually, model-free RL becomes a lot harder because model-free RL at this point has to solve a multitask problem, whereas model-based RL, in a sense, still solves a single task problem. There's still just one physics model governing the writing of all of these digits. In fact, it's basically the same for all the digits. So in this case, model-free RL actually starts to struggle. So this is sort of showing SAC and natural policy gradient, which you can think of the implementation here is basically identical to TRPO. The little green sliver here that gets to maximum performance right away, that's PDDM. So essentially, it's not any harder in this case than drawing a single digit for the model-based method, but much, much harder for the model-free methods. So that's one potential advantage. Another advantage is that this would be preferred when we want to transfer the same dynamics model to perform multiple tasks. So one of the things that Anusha set up is this task. This is kind of a hand exercise. So these are called bouting balls. So you're supposed to spin them in the palm as an exercise of manual dexterity. And what she did is she trained up a model to do this task, and then she used the same model without any additional learning to perform the task backwards. So the only thing that changed here is the reward function. The model didn't actually receive any additional training data. And you can see that it's not perfect, but nonetheless, this neural network dynamics model learned enough about the pattern of context and physics for this kind of object manipulation task to be able to spin the two bouting balls in the opposite direction without needing to receive any additional training data. And also the same exact model can be used to reposition one ball in the palm to different locations. So the red dot indicates the target position, and you can see the hand automatically tilts in order to get the ball in the right place. And of course, as I mentioned before, these kinds of methods can be very advantageous if you want to learn in the real world with a small amount of interaction. So one of the things that Anusha did is she set up real world training for this bouting balls task with a shadow hand robot. And here you can see actually training proceeding in the top left. You can see how many hours have elapsed. This is 30 to 60 minutes into the training process. I can kind of just about do half a turn. After 60 to 90 minutes, it can sometimes do a full turn, but not consistently. After 2 hours, it can do a full turn most of the time. And after 4 hours, which is not shown here, it can do the task very reliably. Now, this is worth contrasting to something like, for example, the concurrent result that came out from OpenAI with the Rubik's Cube, which had one object with articulated parts that required the equivalent of about 120 years of simulated training. This required 4 hours in the real world. What about images? I'll go through this pretty quickly, but the same basic recipe can be used with image observations. With image observations, of course, if you're predicting the future, that means you're predicting images. So you need much larger convolutional and deconvolutional models. So here you can see in each row predictions starting from the same initial state, but for different action sequences. This is a robotic arm pushing objects around on the table. Same basic recipe, same overall algorithmic framework, just a much larger and more elaborate model. And we can do things like command it to move a particular object to a particular location. So here the red dot denotes the object to move, the green dot, the destination that it should be moved to. But crucially, the model is not told anything about objects or anything else other than the world consists of pixels. More recently in this work by Annie Shi, we were able to demonstrate that you could use this to essentially acquire a kind of emergent tool use. So we told the robot to move these two poker chips off of the plate to clean it up, and then the robot figures out using its model that a very efficient way to do this is to pick up the sponge and use the sponge to push the poker chips. Another example, the robot gripper is not allowed to leave the green region, so it has to figure out that it needs to pick up the red hook to move the blue cylinder. And here, the graduate students left some trash on the table, and the robot has to figure out that a good way to push the trash to the edge is to pick up the water bottle and use it as a kind of improvised tool. All right, I'll skip over this part in the interest of time and focus on the next part. So far I talked about how we can do planning with a very crude kind of planning with models trained as deep neural networks, but the skills have still been relatively short horizon. If we want to move to longer horizon skills, we really need to think about getting more expressive primitives and then composing those primitives. So what I'm going to talk about in the next section is actually just how to acquire those primitives. The trouble with long horizon tasks is that if we haven't solved the task yet, it's hard for us to know what primitives would be useful for it. So one way we could approach this instead is to actually learn primitives in an unsupervised manner, essentially learn what you can do in the world without any reward function, and then figure out how to leverage those behaviors to solve more complex tasks. So the question we're going to ask in this section is, can agents invent their own tasks to practice in order to learn about the world? And then in the following section, I'll talk about how after this unsupervised interaction, we can use these skills together with planning methods to solve new, more complex and more temporally extended tasks. So this section, you can almost think about it as the robot equivalent of a child playing with objects in the world. The child is not playing randomly. The child is inventing games for themselves, setting their own goals, and then attempting to achieve those goals. And that's what we'll want our robots to do. So we can cook up sort of a rough outline of an algorithm that does something like this as following. We're going to have two models. We're going to have a goal proposal model and a policy that attempts to reach that goal. And the way that the learning will proceed is first we'll generate a goal, which essentially means sampling a state from our model. The model here is a generative model, so the particular one we'll use is called a variational autoencoder, or VAE, although there are many possible models that could work. So at a VAE, you have a latent code, and then you generate your state as resulting from that latent code. In this case, if our observations are images, that basically amounts to generating an image of a possible state in the world that you would then like to try to reach. So we'll sample from the prior, from P of Z, and then sample an image X from the posterior P of X given Z. And then you'll attempt to reach that goal with your policy. So your policy here will be conditioned on your current state X and your goal XG. And you might succeed or you might fail, but either way you'll get some data, and you'll use that data to update your goal generator just with maximum likelihood, and then you'll update your policy with reinforcement learning. So that's basically the process. You'll just repeat these 4 steps over and over again, generating goals, attempting to reach them, updating your goal generator, and also updating your policy. All right, and now that's a very reasonable recipe, but it has a little bit of a problem, because if you imagine that your robot will generate some goals, try to reach them, and then update its generative model will basically become concentrated around the kinds of states that you've gotten pretty good at reaching. So if you lift up a cup, you see lots of states of the cup being lifted up, then you'll generate more goals for lifting up the cup. And that's no good. We'd like to actually get diverse behaviors and diverse coverage. So intuitively, we can think about it like this. Let's say that we have this 2D navigation task. The circles here denote the states that we visited, and you can see that initially maybe they're all bunched up in the lower left corner. Maybe that was our start state, and we've explored very locally. What we'd like to do is we'd like to pick out those states in the rarely visited regions and essentially kind of upweight them to say, let's go to those rarely visited regions a bit more often. If we reweight the data like this before refitting our generative model, the coverage of our generative model will get a little bit broader, and then next time around we'll suggest broader goals. It turns out that a very simple way to do this is to actually use the density estimates from your previous goal proposal model and weight by 1 over that density raised to some small power. And it turns out that we can actually prove that if we follow this procedure for any power greater than 0, you will actually eventually converge to the uniform distribution over goals on the valid state space. So you will actually get good coverage. And this actually works in practice. So this is an experiment that we did where we took our Soya robot and we placed it in front of a door. Now we didn't give it a goal, but of course you put a robot in front of a door, that's a little bit suggestive, right? You kind of have a particular idea in mind. So we wanted to see if it would learn to open the door, but we wanted to make sure that it could figure this out on its own without actually getting any reward function. So at the beginning, on the left here at 0 hours, a lot of the proposed goals have the door mostly closed, and most of the RL exploration just wiggles the arm in the vicinity of the handle. But after 5 to 10 hours, it pretty quickly figures out that a lot of the rarely visited states involve the door being opened and starts proposing many more goals that actually involve opening the door, such that after 25 hours, it can actually open the door quite reliably. Once training concluded, we gave it a little kind of final exam where we gave it goal images provided by a human that asked it to open the door to different increments of angles. So you can see in the lower right the photograph that we used as the goal that we gave it, and in the large image you can see the behavior that it actually produced. And in all these cases, it was actually able to open the door pretty close to the desired angle. So it actually acquired these skills, and the skills are kind of useful. One little kind of mathematical tidbit about this method is we could ask, what's the objective for acquiring these skills? It turns out that the objective actually has an interesting and fairly intuitive form. So as I mentioned, at convergence, the goal proposals are actually going to be uniform over the set of valid states, which means that we're maximizing the entropy of the goal proposals. That kind of makes sense. You want diverse goals, you want goals to have high entropy. But what does RL do? Well, RL trains the policy to reach the goals. So it essentially optimizes the policy so that the last state is going to match the goal. So S is going to match G. As pi gets better, S gets closer to G. So this means that P of G given S becomes more deterministic. So as you train your policy, it's easier and easier to predict what the goal was from the state that was reached by just saying the goal was the state that you reached. So that's the goal, that's the final state. So that means that you're minimizing the entropy of G given S. You're making the goal more predictable from the state, because if you reach the goal, you can perfectly predict the goal by just saying it's the state that you reached. Now this equation, some of you might recognize, is precisely the equation for the mutual information between S and G. And it turns out that you can show that this method actually maximizes the mutual information between the final state and the trajectory and the goal because it optimizes this difference of entropies. And that's quite intriguing. So maximizing this mutual information provides good exploration, good coverage, and effective goal reaching.
Sergey, sorry for interrupting. We are at about a bit over 20 minutes. Mm-hmm. Just checking in, like how long?
Yeah, this is 30 minutes, right?
Okay, cool.
How much?
Oh, it was actually 20 minutes according to what I have.
Oh, I see. I was told that it was 30 minutes. I apologize.
Okay.
Okay.
So first it was so nice, and now I'm so nasty.
Sorry about that. Okay. Well, I think if we're out of time, then I could actually conclude there, because that's a nice boundary at which to end. I can tell you in less than 1 minute what the high-level idea of the next portion was, which is maybe easiest if I skip the more technical part and go to the really brief slide at the end. So the short version is that these kinds of skills can actually be used in a planning framework. And there's a more sophisticated planning framework that I'll make the slides available afterwards. But the really simpler planning framework is described in this paper by Benjamin Eisenbach called Search on the Replay Buffer, where you can essentially imagine forming a graph out of these goal-reaching skills. So you can imagine that if you have a bunch of states, you can plan between those states, and a skill that you acquire that is able to reach goals can serve as the local planner in a graph search. So the cost on the graph is provided by the value function for that skill. And where do you get the nodes for the search? Well, the nodes can actually come from the replay buffer that you use to learn those skills. And that turns out to be quite nice for learning longer horizon behaviors, things like navigation skills. So I don't have time to go through this, but in the paper we had some illustration of this being used for vision-based planning in indoor environments. All right. Sorry again about the timing snafu, but thank you very much for listening, and I'd be happy to take questions.